right? He's the first person on the timeline. He came up with the
Oh,
atom.
making a timeline.
Right, because Aristotle obviously didn't believe in the atom. He thought earth, fire, air, and water. And then, comes along Antonio Lavoisier. And Antonio Lavoisier, he's the one who said, okay, air is a mixture, right? He found oxygen. So there were several people that disagreed with Aristotle. So we have time. That's kind of a review. We're getting close to the end of the year, so we're just reviewing some things. Over here, we have bell work. Number 1, what kind of bear dissolves easily in water?
Polar bear.
Ah, polar bear, yeah.
I heard that joke.
So the point is that water is like a what?
Okay.
Starts with an M, sticks to things.
Moisture.
Huh?
Starts with an M and it sticks to things. I don't have any here right now, but if I had something to stick to this and start, yeah, it's like a magnet. That's why water sticks to things. If you take a shower, it sticks to you because it's polar. It's like a magnet. It sticks to windows.
A shark.
Shower.
Oh, I like watching it like run off.
Sorry, I had a little denture problem. My
Oh,
teeth
when I
are
was taking a shower,
moving
I
around
closed the curtain
in my
and
mouth.
water was running down my arm and it started running out into the floor.
Shh.
I like doing this, so I don't like
Shower. Okay, so water will stick to you in the shower because it's magnetic in nature, polar. Now,
Wait, is our skin polar?
Doesn't it like stay in ballpark because it wants to be like with itself and not like anything
No.
else?
right, water tends not to stick to oil, so
Yeah.
that's why they separate. Oil and water separates because of polarity. Yeah. Oil being nonpolar, and a good example that from yesterday was the carbon-hydrogen bond. We talked about if you subtract the electronegativity, 2.5 minus 2.1 gives you a 0.4 value for the hydrogen bond, and that means it's nonpolar. So your hydrogen-carbon bonds are going to produce nonpolar environments. So most fats are carbon-hydrogen bonds. Now, if you eat pig fat, do you store pig fat in your body, Eliza? No, you do not. What do you do with it? No, you break it down and then you store it as human fat. You have to make your own fat. You can't store pig fat, chicken fat, any fat other than your own fat. So keep that in mind. All right, number 2 up here. Name the 3 bond types that electronegativity difference calculates. Name the 3 bond types. We talked about them yesterday.
Oh.
That electronegativity difference calculates. Nonpolar.
Non-polar, ionic.
Ionic. Very good. So a little bit. Trying to do the timeline.
You know, I didn't do it right, so.
Sophie, she's almost done. So I'm only going to give you about another minute or so. Then we need to head on over to the lab. You're supposed to. I'll let you finish in the lab if you have. Okay, so Hannah made a nice attempt on her timeline. She got Democritus towards the end. Actually, he should be up here in the front. I gave you yesterday a JJ. If you just Google these people and their images, you'll see this thing that Democritus is wearing is some type of fur coat. Families of elements, experiment example. So we're looking at like water. Now, hydrogen is diatomic. What does that mean? Hydrogen is diatomic. What does that mean?
Huh?
Hydrogen is diatomic. What does that mean?
Oh, you know, I learned this last year, but you know.
I forgot what diatomic is.
What does di mean? No, it means 2. It means you have 2. So diatomic means you have
Diatron. That sounds very wrong.
you have 2 hydrogens. So over here, this is kind of just an example. This is not how hydrogen normally is. I'm just giving this example to you because it's simple. Most of you have seen water before. So oxygen up here is diatomic as well. It's O2. Now in this situation, if I took 1 hydrogen and 1 oxygen, I would not have water. All right. If I took 2 hydrogens and 1 oxygen, I would have water, H2O. So this would be the largest amount, so this would be the right ratio, the right proportion, 2 to 1, right? And then if I had 1 hydrogen and 2 oxygen, I would not have water. So that's what you're doing today in the lab. You're going to determine the formula based on the proportions. So you have this well plate, and it says here you're going to put 11 drops of your silver nitrate in the first well plate, and then 1 drop of the potassium chloride. So it's 11 to 1. And then you're going to put 10 drops of the silver nitrate, and then 2 drops of the potassium chloride. And you continue doing this until you get to 6-6. So you take 6 drops of the silver nitrate and 6 drops of the potassium chloride. The first one, this should be the most precipitate. So I'm giving you the first answer. Look for this. You should see the most precipitate here. Then you write on the proportion blank on the back side of this, it says proportion. You're going to write 6-6, or that simplifies to 1-1. So by clear. Then over here it says formula. Well, if I have 1 silver, right, that would be Ag, and 1 chloride, that would be Cl, so it's silver chloride. Now on the periodic table, the element for Cl is chlorine, but when chlorine binds with something else, it's called chloride. It changes its name. That's how we know that it is not chlorine anymore. It's bonded with silver, so it's silver chloride. It's like 6 is the
6 is the highest peak.
yeah.
Stop. No, he's turns.
Yeah.
1, 2, 3,
Oh, I think I did 11
5,
instead of 10.
6, 7, 8,
So I was thinking,
9,
oh, well.
10.
I'll just do one of these.
Are you supposed to add both?
Well, there are only 3 accounts up here. Lad, Gilmore, and Weston. Dude.
My bad, bro.
What kind of bear dissolves easily in water, Chris? Hello?
We talk about animals.
What kind of bear dissolves easily in water? Hello?
Talking about animals and
Chris? No, you said polar bear. Polar bear. Why? Because of like dissolves like. Polar, water sticks to things because it's like what? It's like a magnet you stick on your refrigerator. So it'll stick to you because of that. Water does. And what that means is that water will dissolve things that are like it. So if you're magnetic, it's going to stick to things that are magnetic. If you have a stainless steel refrigerator, will magnets stick to it? No. Yeah, stainless steel is not magnetic. Magnets don't stick to it. So stainless steel would be like oil to the magnet. They repel each other. They don't mix. Nice job, Gillian, with the order. You have Dalton second, which is correct, but he actually looks like this. If you look online, you'll see his picture right there, and it looks more similar to this right here. Kind of got the V-neck there. V-neck, kind of the hair parted. I don't really see him similarity with that picture there. Excellent job, Rain. Nice start with the people, getting them in the right order. Yesterday we learned about electronegativity, and that you have 3 different bond types that can be calculated with it. The polar covalent, the non-polar covalent, and the what? What was the last one? Anybody remember? Starts with the I. The ionic, very good. Now what you're going to do today in the lab, you're going to look at families of elements. So if we gave an example up here, this example is not necessarily real world. That is, you're not going to do this in the real world because hydrogen is diatomic. What does that mean? It doesn't exist by itself. It has H2. Di means two. So it's found as H2. Now up here, Hope, people have seen H2O before. So we're looking at here proportions. If you have one proportion of H and one proportion of O, that's HO. That's not water. If I have two proportions of hydrogen and one proportion of oxygen, that's H2O. It's a 2-to-1 ratio. There's two hydrogens per one oxygen. And then over here, if I had one hydrogen and two oxygens, I'd have no water because that would be a 1-to-2 ratio. H2O. Does everybody see how that's a 2-to-1? H2. Now we would typically write it, this is a coefficient, not a subscript. The subscript would be this right here, H2O. So that's what you're going to do today in the lab. You're going to take silver nitrate, 11 drops. So underneath the well plate, you're going to see numbers. And that's the number you're going to use in each well. 11 drops of the silver nitrate in the well number 1. Well, number 2 is 10 drops. Well, number 3 is 9. So it decreases all the way to number 12 where you don't have any. Number 11, it's 1 to 11. So 1 drops of silver nitrate, 11 drops of potassium chloride. So what you're going to make here when you mix these two, when you mix silver nitrate with potassium chloride, you're going to get silver chloride. Why? Because silver is a better provider. Now the question is, what's the proportion going to be? What's the formula going to be? Silver won't tell you because it's a transition metal. If you look up on the overhead here, it's showing you right here that silver has many different states. It has a oxidation state of 1 positive, 2 positive, or 3 positive. So which one's it going to be? Well, you have to look at the non-metal to tell you. So the non-metal is going to tell us in this lab by the largest amount of precipitate. So I'm doing the first one for you. You should see the largest amount of white substance, which we call precipitate, in the 6-to-6 ratio. This should be the largest amount. And because of that, it's a 1-to-1 ratio, and it's telling us the charge on the silver. So we don't know what silver is going to do. We have to look at the chlorine to tell us. So that the silver is 1 positive because of the chlorine of this 1-to-1 ratio. It could have been 2. You can make AgCl2. It's possible to make that. It's also possible to make AgCl3. But you have to have the right conditions. You have to have a different temperature, different pressure. We don't have those conditions today, so we're making AgCl. Is everybody clear? So you're going to follow this pattern to get the formula. Now this one is Ag, that's Br. This is AgI, this is AgS. So you're going to determine the formula. They're not all going to be 1-to-1. Now be careful with the silver nitrate. If you get it on your hand, it will turn your skin black. It basically kills it. Nice job, Sierra, with getting Democritus, John Dalton, Thomson, Rutherford correct. The Schrodinger model looks more like this. It really related to the planetary model. Raise your hand. Raise your hand. Vance? A polar bear. Yes, a polar bear dissolves easily in water because Alright, 4th well plate. 8 drops of silver nitrate, 4 drops of the potassium chloride. All the way to the 6th well plate where you have 6 and 6. Now at the 6th well plate, you should see the most cloudy or the most precipitate at the bottom of the well plate. So at the bottom of the well plate, if you could turn it to the side, you would see a liquid, and at the bottom you're going to have most precipitate. This is called a precipitate. Basically, it's a solid that forms at the bottom. So the most that forms tells you your ratio is correct. As you see over here with hydrogen and oxygen. This is an example. This isn't found in nature. You don't find hydrogen by itself. It's diatomic H2. You have O2. But just to show you the ratios, 1 to 1, 1 hydrogen to 1 oxygen is not water. 1 hydrogen to 2 oxygen is not water. It has to be a 2 to 1 ratio to make water. This is going to make the most water. Does everybody understand? That's kind of what you're doing today. 2 positive or 3 positive. You can look on Wikipedia. I've showed it to my last period class. But I just want you to know what this looks like. This looks like the 1 electron around it, 2, and then 3. Now, chlorine is going to determine what the formula is. It could be really any of these 3 if you had the right conditions. So the conditions in the lab is going to dictate which precipitate is the most. I'm telling you the answer for the first one. It's going to be 6:6. The ratio, this is the answer for the first one. It's 6:6:1:1. Cloudy, you're going to describe the precipitate as being cloudy. So what does the formula look like? Well, it looks like this here, 1 Ag, 1 Cl. Does that make sense? Now, if you're looking at the electron dot, you're going to take one of these, right? One of the Ags, and it's going to be AgCl. Then you're going to have your Cl. That's what it's going to look like.
Did you add what was supposed to be in there? Thank you. I always make these really sweet short. No.
Claire, do some work.
Do I look smarter with these glasses on?
Amazing. I know, you blessed.
Remind me not to aid for you.
Thank you. Artists, John Dalton, J.J. Thompson, look, Niels Bohr, that's Schrodinger. Who's this person? Ernest Rutherford's one of them. Ernest Rutherford's one of these. I think Ernest Rutherford. Is that Rutherford? Yeah, that's Niels Bohr. This has got some nice color on hers. I believe this falls under Ernest Rutherford, and this goes over here. Schrodinger had the planetary model. No. Naomi? No. Madeline? The polar bear, very good. Now, it dissolves in water because, why?
How does a polar bear dissolve?
Got Melanie? It's polar.
But it's a bear.
Right, but water is polar, and then it sticks to things. A lot of people think water's wet. Water's not wet. It's polar. It sticks to you. It sticks to the window. It sticks to your shower. It sticks to things. And because it sticks to things, it dissolves things that are like that. So, polar, bear, that's the thinking. It's a joke.
I don't think this is cleared out all the way. Wouldn't we already be doing this?
We do have some cleaner that you can use.
We need that. How we clean?
Purpose. I'm just gonna gonna start doing this.
Hey, Miss Thompson. What is this for right here?
Power, electricity.
This one, not this one, that one. What do you mean?
All right, so once again, Jimmy's done a nice job on the board. 66 1-to-1 ratio. This should be the most concentrated, and it looks like it is. Obviously, compared to this one. This one. Yeah, the most concentrated gives you the ratio. Here's the AG BR2.
Did y'all both know over the white shit?
Yes.
Okay.
This one and this one look like the most concentrated.
Okay.
Got the silver iodide one here. Make your decision about which one you think is most concentrated. This is the sulfide. So this is sulfide. This is iodide. Yeah. Iodide. Sulfide. So which one do you think in the sulfide is the most concentrated?
This one or that one?
Okay. Melissa, you're doing a nice job there.
I think I messed up.
Uh-oh.
Wait, was that supposed to be extra? No. Shoot! Oh. Take your point.
Go with lady first, Alex. Polar bear. Now, water is polar. It's not wet. That means it sticks to things. It's kind of like a magnet. Now, raise your hand if you have a stainless steel refrigerator. Very good. Now, magnets, will they stick to that? Raise your hand. Will magnets stick to stainless steel? No. No, they will not. Difference calculates. Kunik? The third one starts with an I. Isn't it what? Ionic. Very good, Josh. Ionic. Now this chemical is in a white plastic bottle. If you get this on your skin, it's going to kill your skin. It'll make it black. Don't panic. It will come off. I'm just telling you what it will do. It'll kill your skin cells. No. Because... No. Just be careful with it. I'm just telling you what it'll do if you get it on your skin. Now, this is what you're testing everything against. It's the silver. Now, this one is potassium iodide. This is part of the halogen group, and these all have a set molar concentration. So when we do these ratios, one's going to be excess, one's going to be limiting. So when you have 11 drops, like this first one up here, this 11 drops, that's going to be excess. One drop is going to be limiting. Does everybody understand? If you're baking a cake and you have excess compared to limiting, you don't have enough eggs, you have more flour. So one's excess, this will be excess, the first one, this will be limiting. The goal is to get where they're equal. I'm going to tell you the first answer.